Here's a question here by the scientist, 5.2. It says a person of mass of 50 kilogram climbs on the top of a mountain which is 6,000 meters above ground level. State Newton's laws of universal gravitation in words. Let's give it in the form of an equation. So we're giving the gravitational force. It's given by the big G. It's going to be mass 1 multiplied by mass number 2 divided by the R squared. So it is this. This is the definition of it in a formula form. But then in words, we could say in the universe. You have to understand it's in a universe. It's not only on Earth. In a universe, two objects attract each other with a gravitational force which is directly proportional to the product of their masses or the multiplication of their masses and inversely proportional to the square of their distances from their center or from their equivalent points. Doesn't have to be center. The point, it must be, the points should be equivalent. So center and center is also equivalent. So this one you'll say center. But then if we're doing Coulomb's law, you can't say from their center because you're dealing with charges. You should use the word between them. But I've seen books saying between their center, which is nothing else but garbage that needs to be thrown in a rubbish bin where we throw the cabbage and the garbage. It rhymes, isn't it? Cabbage, garbage. All right. Fine, those is it. All right, now again here, they say calculate the difference in the weight of the climber at the top of the mountain and at ground level. All right, this is good news because they just told us the number is above that. They should have told me where he's at, but here's the thing. All right, so when there is a height, you need to actually know, which planet you're dealing with. All right, so now let's talk here. Calculate the difference in the weight of the climber at the top of the mountain and at ground level. I don't know what planet are we're dealing with for that M. All right, but I'm going to just draw two scenarios for you to understand. Scenario number 1, this is what you have. I'm going to use a white dot to represent a person. This is the person not on top of the mountain. That's why I don't like that R, because it makes people think it's a radius. It's not the radius. It's a distance between them. So I'm going to put a D squared there. All right, so in this case, the distance from the center of this yellow planet to that white object, the person, so that is R. So in this case, the R will be equals to the D. Then we repeat the same scenario. We have that person, but now remember there's like some kind of a mountain there, and the man is way up there. Then the distance from the center of the planet to that person is going to be the radius plus that 6,000 meters. So therefore the D will be whatever the radius was plus the 6,000. All right, so this is what we've got. Now we need to understand one thing, what's happening here. The radius has been, or in other words, the distance has been increased by a certain amount. If we're dealing with planet Earth, I will actually divide the new D. Let's call this one D1, and this one will be D2, to check by what scale did they multiply that. Maybe we double the distance, maybe we half it, maybe we triple it, or whatever it might be. All right, so now, assuming if it's planet Earth, then you've got the data for this. Assuming it's the sun, you'll be given the data for that. All right, because here, I don't have a specific data given to me. We can assume it's planet Earth. It doesn't matter which one you're dealing with, as long you can check at the R. All right. There are many ways to do this. One way to do this was to do this. Like I said, I was going to take distance 2 divided by the distance 1 and see by how much was the other one multiplied. All right, but then if you're to calculate each one using that formula and that one there for the second one, you can subtract the 2. All right, first let's say this is going to be the gravitational force. Allow me to use 1, meaning using the first data. So I will have the big G, I will have mass 1, and I've got the mass of the guy, which is 60 kg, and then I will divide that by the D. In this case, the D will be R squared. And you punch that, you get the first answer. And then the next one, you'll say, okay, now I've got the gravitational force for the second scenario. So again, it's going to be big G, and I'm going to take mass 1, and then the mass of the person does not change, it's still 60 divided by, but this time the scenario changes. We're now having R plus the 6,000, close the bracket, all squared. Now, since they asked me the difference, there's many ways. Difference you can subtract, because the mass becomes greater, the weight becomes greater when you are closer. So this one is actually big. That's why a paper can fly away when it's far away from the ground. But when it's next to the ground, it's stuck. This is big. This one will be small. Well, you can even see it mathematically. When you increase the denominator, the final answer becomes small. So if you wanted the difference in those one, I'll say the difference. One way you could have written it as Fg of the second one, and then, which is the gravitational acceleration, minus the F subscript G. I'm sorry, it's the other one. It's the other way around. I must put the big minus small. So it's the first one. Yeah. And then minus the Fg of the second one, and you try to work out all of that stuff. But another way, we can divide the two ratios and see how big is the other compared to the other one. So in other words, if I say big divided by small, meaning I'm going to take Fg1 and then I'm going to divide it by Fg2, and then it will be, well, if you had the values, you would have worked it out. So I'm not assuming it's Earth. I'm just assuming it's whatever planet it is. You are going to take the first one, the white one. I'm just going to copy it as is so that I can plug it in here. I plug it there, and of course it will be divided by the yellow one. So I'll take the yellow one there, and then I'm going to put it there. All right, but then mathematically, you can make this a multiplication. When you do that, this turns upside down, and you can see that will cancel that. You're left with that divided by that. I want you to see that. So now I can now write it as, in this case, the R plus the 6,000 all squared divided by the r squared at the bottom. So this is FG1, and then this one will be FG2. You cross multiply, so you can see that the force of gravity for the first one will actually be R plus 6,000. I'm going to square that, divided by R squared times greater the second one. So which means this one will be this one. So therefore, if I were to use this again, then I'll say, the difference, I'm doing it symbolically. If you had the values, you'll just put them in. It will be straightforward. Then I say, FG1 it's actually this one. So that one will be R plus 6,000. And I'm going to close the bracket. Is the bigger one squared divided by the R squared. FG subscript 2 minus FG subscript 2, of which if I want to pull out a common factor, I can. I'll say it will be FG subscript 2 into, let's use the brackets themselves, which is this one. These are brackets, and these are parentheses, R plus 6,000 all squared divided by the R squared, then minus the 1. That will be the answer. You just put all the values and then you're okay. I did it. I didn't want to use planet Earth because it will be straightforward and easy. All right. If you had you used planet Earth anyway, you will just put the values here, work out the difference there. Here I worked out by how much was the force greater compared by that, and we also used that one there. Thank you very much.